welcome to this new video on specific heat from solid bodies and fluids. In the previous video we talked about CV and CP values, which are the specific heats at constant volume and constant pressure, and we also wrote some sort of equation with CP and CV values for adiabatic processes. Now it's just gonna be a small introduction to CP and CV values. It can obviously also be derived from statistical mechanics, statistical physics in general. However, here we are just gonna talk about how it is motivated through experimental processes, and just to give you an idea of what the specific heat actually is for at least the axiomatic part of thermodynamics. Right, so we begin with our first law of thermodynamics again, which is that delta E is equal to delta Q plus delta W. Obviously, these are not the same deltas as we talked about. These are not state variables. Right. So if we now take a cylinder or like some kind of solid body whereby the ends are totally blocked, so there can not be any change of volume, there cannot be any kind of change of pressure. Rather, there will only be an exchange of heat through the walls. Right. So if we now say that since the volume and pressure cannot change, that the delta W is actually equal to 0, and we give some kind of heat from outside, whereby the heat is obviously bigger than 0, so like a positive value of heat that we give. So in that case it would obviously be that the delta E would be right equal to delta Q. Now we can obviously see through experimental processes at first that this delta Q, it will increase as we increase the temperature. So it would be obviously directly proportional with the change of temperature. I have to again stop writing the deltas in this way, because again it's not a state variable, so I'll just change them. And it has obviously a proportionality with the change of temperature. The amount of heat would also actually be like the change of the amount of heat would also actually be proportional to the amount of stuff that's inside, so the mass of the stuff, as well as the number of moles of the substance that's inside, or the number of particles which are inside. So in total we can also write that delta Q is then proportional with m, which is mass obviously, or delta Q is then proportional with the number of particles, or delta Q is then proportional with the number of moles of stuff that's inside. So all in all, we can see that the delta Q is then proportional with let's say mass and delta T, or delta Q is actually then proportional with the number of moles of stuff times the difference of temperature. And what do we do when we have a proportionality that we want to remove? We remove the proportionality by multiplying the variable on the right with a constant. So we have the delta Q, which is equal to, let's say in this case, a constant C times m times T, like delta T, or the molar variant of this constant times the number of moles times the change of temperature. So how will one write this constant? We can change this equation to represent C is equal to 1 divided by m, change of Q with respect to change of T. This is a very, very useful, this is going to be a very, very useful pattern that we are going to see also later on in our Carnot's principle and the Carnot's process. We are going to come back to it later on, but for now it's very important to note down that the constant can be written like this, which is basically proportional to this term here, which is the change of heat, the heat that is added divided by the amount of change of temperature. And this C is basically the specific heat. And the molar variant of it will be then the molar specific heat. For example, water, we can go for some examples. Water, for example, will have a C which is around 4,185 joules per kilogram Kelvin, or which is similar to the molar specific heat of which is basically the molar mass times the specific heat, would be around 75.3 joules mole Kelvin. Right. And for gases, obviously for any kind of ideal gas, it can be just defined as like it can again be proportional to the change of heat divided by the change of temperature. Right. How are they officially defined? We already talked about a formula whereby we considered C is equal to F divided by 2R, where we talked about the F as being the degrees of freedom, F being the degrees of freedom that an ideal gas has. And what it actually is, this C that we see here is actually a CV, which is basically the specific heat at a constant volume. I can write it down also. Specific heat at constant volume. And it is officially then also defined as something like this, where R is the universal gas constant. And well, I'm not going to write the value of it. You guys can Google it out. But yeah, it is then defined like this. How that description came to being, how this formula came to be, we can also talk about in a different video. This video is supposed to be just a motivation as to what the CV and CP values are physically, what they physically mean. And we also have a variant of the C value in terms of pressure. And that is, as you probably also like back calculated from the last video, it is F divided by 2 plus 1 times the universal gas constant. And this is basically specific heat at constant pressure. Right. And as you would understand from these two formulas, that basically Cp is equals Cv plus R. It is obviously also very important to note that these are the molar variants of the C values. And again, we talked about F being the degrees of freedom, and we also talked about the example of single atomic gas, a monoatomic gas, where it has the degrees of freedom according to the coordinate axis, because it can basically move everywhere. And it would be then F would be equals 3 for a monoatomic gas. So the CV value for a monoatomic gas would basically be 3 halves, so 3 divided by 2 of R, and the CP, again the mole variance of them, mole variant of the CP would be 5 divided by 2R. Right, so much as to the motivation of why CV and CP, what CV and CP values actually mean. We are gonna talk in the next videos more about how they can be used in different cyclic processes. But as for the derivation of it, we will come back to it later on in some video when we have learned a bit more about statistical physics. So thank you again. Please like the video if you do like it, and share it with your friends if it helped you, and please comment on what should be changed in such videos. Thank you.